Today we're going to talk about synthetic data generation in Python, and this video today is going to be quite technical. We're not going to focus on LLM-based data generation. We're going to focus on classic methods, classic machine learning methods. Classic still means we're doing neural networks, but we're not doing transformers. We're not just going to pull a model from Hugging Face. And specifically, we're going to focus on synthetic tabular data generation using CTGANs and TVAE. So these are conditional tabular generative adversarial networks and tabular variational autoencoders. We're going to talk about the architecture, we're going to talk about how they work, when to choose what, and then we're going to look at code samples. So this video contains multiple parts. We're going to start by talking about the idea of synthetic data generation, when is it needed, what are use cases for it. Then we're going to talk about the state of the art, how it is done for tabular data nowadays. We're going to talk about the research state of the art and the practical state of the art. Then I'm going to briefly talk about the basic idea of the architecture of the two things we're going to use, which are, as I said, CTGANs and TVAEs. We're going to talk about that, and then we're going to get into practice, into actual coding to show you how this works. You can, of course, skip the individual sections if you're not interested in the theory, you just want to see how it's done in Python code. You can, of course, skip to that section, but this video today is going to be very educational, so stick around, and if you like this video, let me know by hitting the like button and subscribing. But now, let us get right into it. Alright, so we're going to talk about synthetic data generation in this video today, and we're going to learn how to do it in Python. As I already mentioned in the introduction, this video is going to be split up into multiple sections. We're going to cover some theory first. Later, we're going to go into the practical part. If you're only interested in the Python code, if you're only interested in the implementation and application, you can jump to the respective section by clicking on the timestamps in the description down below, or also at the bottom of this video in the timeline itself. You can just jump and skip the theoretical part if you're not interested in that. However, if you actually want to learn what we're doing here, if you actually want to understand what's happening, I would recommend also watching the theoretical part. But of course, the audience might differ. Some people might be interested in learning stuff. Some people might only be interested in the application. So you will find the chapters in the description down below. And for the theoretical part, this is going to be my fancy setup, some slides, as I would like to call them, here on the right, some keywords that are going to summarize what I'm talking about. And I'm going to, if needed, to do some visualizations here on the left. And the first thing I want to cover here for the context of this video is we're not going to work with LLMs today. This is not LLM-based synthetic data generation. We're not doing anything like model distillation or text or image classification or prompting LLMs to generate synthetic data. We are using more classic approaches. Classic still means we're using deep learning, so neural networks, but we are going to be using CTGANs and TVAEs. I'm going to explain what they do in a second here. This is basically conditional tabular generative adversarial networks, so GANs, generative adversarial networks. And here we have variational autoencoders, and this is also tabular. So tabular basically means that the data we're going to synthetically generate today is tabular data. We're not generating time series. We're not generating audio, images, or anything. We're generating basic tabular data. So a classic data set, something like the California housing data set, where we have maybe median income, then we have, I don't know, square meters or something. I'm not sure what the columns were of the California housing data set, but we want to artificially or synthetically generate data rows. What does this exactly mean? This does not mean that we're just randomly generating values. We don't just have the columns and the data types and then we just do a random number generator or a random generator in general. What we're doing is we're training models to learn the distributions and the patterns and the relationships in the data, and then we use these models to generate synthetic data. So we feed in actual data. This is actual data from real people, from real houses, whatever. We feed that data into a model. The model learns the patterns, and then the model can generate synthetic data. This is not the best visualization here, but that is synthetic data. So data that looks like real data, but is not real data. And the use cases, as you can see here on the left, there's different use cases for that. Sometimes you just don't have enough data, so you need to artificially create more data to have at least some data to train on. Sometimes, however, it's not about not having enough data. It's more about a privacy concern. So you might have enough data, but you don't want to publish the actual data because it might be sensitive. So let's say you have your data here, your company data, which is quite sensitive. And then here there is an ML engineer who wants to train a model or do some data analysis, you don't want to give the data to the ML engineer because it's too sensitive. So what you can do is you can train a model. This model can generate synthetic data, which has the same patterns, and then the ML engineer could work with that data. This is just one use case. Again, the other one would be we don't have enough data. Another thing is also making data sets and pipelines more robust, meaning sometimes we might have to, or we might want to balance classes. I might have a data set with binary classification, class 0 and class 1. And let's say class 0 instances are 258, and then class 1 instances are 50. Then I might train a model to generate the data based on this real data, and I might artificially generate instances of class 1 so that I have more instances of class 1 when training to not have this skewed distribution here when it comes to the target variable. Another thing would also be to emphasize rare cases in general or to test edge cases. So maybe I have a model that already is trained and I want to artificially generate synthetic edge case data and feed it into my model for prediction to see what comes out so that I can test what happens when I feed synthetic data or edge case data that looks like the real data into the model. That would be the basic idea of what we're doing here with synthetic data generation. One important thing, data generation or synthetic data generation is not the same as augmentation. So we have two different concepts. One is the one we're talking about today, synthetic data generation. The other one is data augmentation. And data augmentation, I also have a video about this on my channel, but data augmentation would be something like I have images of cats and dogs, whatever, something like this, and I'm applying simple transformations where I'm adding noise. So maybe I'm adding some noise to the image and still want my model to be able to classify this correctly. So I take my existing training data and I add some noise to make it more difficult. So I make the model generalize better, or I apply some basic transformation stuff. So the image now looks like this essentially. That is the idea. So I'm doing rotations, I'm cutting out stuff, I'm applying filters. That would be data augmentation. I'm taking real data and adding stuff to it, applying basic transformations to get more data to make the model more robust. Here, however, we're training models, generative models, to actually create new data from the distribution, sampled from the distribution that is learned from the actual data. Now, let us briefly talk about the state of the art and the architectures that we're going to use today. The current state of the art here, the research state of the art, is focused on diffusion-based models. So we have here TabSyn, we have TabDiff, TabDDPM. These are the research state of the art. These are the best performing models if you look at the benchmarks, if you look at the tests. But these are not the models that we're going to use today. On the one hand, because the implementation is more difficult, and on the other hand, because there's also a, so to say, practical state of the art, not necessarily in terms of research, the leading models, but still the ones that are practically being used because they're easy to implement, easy to use, and still perform quite well. And these are the models here introduced by this paper, Modeling Tabular Data Using Conditional GAN. This introduces CTGAN and also the tabular variational autoencoder. Don't worry, I'm not going to read the paper to you. I'm not going to explain all the mathematics here, but I will explain the basic principle, and I'm going to focus specifically on the CTGAN and the tabular variational autoencoder. We're not going to talk about diffusion models in this video today. As I said, on the one hand, because the implementation is more complex and there would also be more to cover here, and also because this is a very good practical state of the art, I would say. So let's close this and talk about the CTGAN first. The CTGAN, as I said already a couple of times, stands for conditional. This stands for tabular, and GAN stands for generative adversarial network. So GANs are usually well known. I'm not sure if most of you guys know what GANs are, but GANs are an architecture where we have a generator and a discriminator. And they basically improve one another via competition. The generator tries to generate synthetic data, or fake data, you could say, and tries to make it look realistic. It tries to make it look like actual data. And the discriminator basically has to take this data and say it's real or it's fake. So the discriminator is trained to distinguish between real and fake, real and synthetic, and the generator tries to make it as realistic as possible. So if the generator is better than the discriminator, it's going to fool the discriminator, and if the discriminator is better, it's going to recognize when the generator generates synthetic data, and they both improve one another. That's the basic idea of a GAN. Now, conditional means that we can fix certain attributes. So I can say, for example, if I have a data row about a house or something, and there's the country of the house, then I could say that I want to generate synthetic data, but I also want to fix that the country, for example, of my house has to be UK. Everything else can be sampled from the distribution that you learned, but I want the country to be UK. So I can provide that as a condition in the architecture. I can force this to be the case. I don't have to filter afterwards. I can say, this is a condition. I want you to generate that, and it will do that. And the T stands for tabular. It just means that we have some tabular specific optimizations that were a problem in the past when it came to synthetic data generation, tabular synthetic data generation. If you want more details about that, I recommend you read the paper. So in a nutshell, it's basically just a conditional GAN, if you know what that is, optimized for tabular data generation, synthetic data generation. Now, the second architecture is the TVAE, which is the tabular again, and then variational autoencoder. Variational autoencoder. And for those of you who don't know what an autoencoder is, basically it's a network that looks roughly like this. You have a bunch of neurons here. You have the same number of neurons on the other side, and then you have multiple layers, you know, like other neurons here. And on both sides, it gets narrower and narrower. And in the middle, you have the bottleneck, you could say, which is the latent representation. So this is the compression, you could say. We're trying to compress data into a latent representation, which means into vector space. And the idea here with a variational autoencoder for tabular data is that we're learning to represent the data in this latent representation as a probabilistic latent representation. So this basically means we're not learning actual vector representations. We're learning statistical probabilistic representations, which means we have a mu and we have a sigma that we learn. We learn the average and the standard deviation, so to say. And I already wrote it down here so we can read that. We turn the data rows, the normal data rows, into numerical representations. So we have numbers. Then we encode them. This is what the autoencoder actually does. This is what it trains to do. It takes these numerical representations as input, turns them into this probabilistic latent representation. And then what we do is we sample from that distribution, from this mu and sigma distribution here, and we try to create new data here. This is our output is going to be synthetic data. So again, what is happening? We're taking real data, we're feeding it into the autoencoder. The encoder side turns this into mu and sigma. Then we sample from this distribution a vector z, and this vector z is decoded into the synthetic data. And there's also a quirk in here, I wrote it down here, that it's done, the training is done in a way that these distributions, the distribution resulting from mu and sigma, is close to the normal distribution. So we have a constraint that makes sure this is the case. And once the training is done, what we do is we take the decoder, so only that part here that turns z into synthetic data, and we sample z from a normal distribution. This is when we do inference. So not from mu and sigma, we sample from normal distribution, and then we get synthetic data based on the decoder trained parameters, or based on the parameters that the decoder learned during training. Now, one downside when it comes to the variational autoencoder is that it doesn't have any possibility to provide conditions. We cannot say I want a country to be UK. So what we would have to do if we want to actually get a certain output, if you want to get, for example, the country being UK, you have to generate, let's say, 1,000 rows of synthetic data, and then you have to, if you want to have 50 where the country is UK, you just have to filter 50 rows where a country is UK, and then you're also not guaranteed that it's going to exist. So maybe you have to keep generating until you get it. Especially with rare values, this can be a problem. So this is something that the GAN is better for, the CTGAN is better for. You can specify conditions. As a general rule of thumb, if you need a quick guide for making the decision, CTGANs are better if you have complex categorical patterns and imbalanced categories. We have the conditional generation that I already mentioned. Whenever you have a lot of categorical columns that are complex, I would use a CTGAN, or you should use a CTGAN. And the more data you have, the better, the more attractive the CTGAN becomes. Whereas the TVAE is simpler, it's more stable during training, faster and easier to tune. You can work with it if you have less data. You don't have to worry that much about overfitting. and it's good for smooth continuous patterns. These are the basic, in a nutshell, decision guides. All right, so now we can move on with the practical part, with the coding part. And for this, we need to set up our environment first. We need to install some packages. For this, you can do this however you want. I recommend opening up a terminal and typing pip or pip3 install, and then the packages we're going to need here in a second. I myself am going to use UV for that. I just like to use the Rust-based package manager UV. It's faster, it's easier to use. So what I'm going to do is I'm going to go to my tutorial directory, and instead of saying pip or pip3 install, I'm going to say UV init and then UV add. But besides that, everything is the same. You just have to say pip install or UV add, whatever setup you're using. And the package that we're going to use for the actual synthetic data generation for the models is going to be SDV. This is Synthetic Data Vault. This is a Python package that offers implementations for CTGAN and for TVAE, so we can easily use the two models that we talked about without having to implement them from scratch. This is the package that we're going to use for that. In addition to that, we're also going to use other packages. So we're going to say here UV add SDV. We're going to say pandas because we want to work with data frames. I'm also going to install scikit-learn just to get the data set and also to do the model training on the synthetic data. And we're also going to use Jupyter Lab. Jupyter Lab is just an environment that allows us to work with interactive Python notebooks. I'm going to say UV add all these packages. Again, in your case, if you're not using UV, just pip install SDV, pandas, scikit-learn, Jupyter Lab. And once everything is installed, we can run Jupyter Lab. In my case here, I have to say UV run first. If you're not using UV, you can just say Jupyter Lab like this. Again, in my case, UV run Jupyter Lab. And this is going to open up Jupyter Lab in the browser. And we're going to be able to create interactive Python notebooks. Now, if you've never worked with interactive Python notebooks, they're quite easy to understand. You create a notebook which has the ending IPYNB. And instead of just running individual, or instead of running the entire script from top to bottom, you run individual cells. So I can say A equals 10, then I can say print A, and then I can say A plus equals 10, and then I can run this again, and you can see it's 20. I can run this cell multiple times. I can then run this cell. So these are individual cells which share the same kernel, the same runtime, but this makes it easier to play around with packages to learn stuff, to visualize stuff, to train models and use them. So that's what we're going to be working with. Now, let us start with a basic example of just training a random forest classifier on the breast cancer data set. We're going to do that with the normal data set. This is the classic machine learning example, nothing fancy about it. And then we're going to see if we can improve the model or how the model performance changes when we use synthetically generated data. Now, I can tell you right away, there's no guarantee that this is going to be positive. It doesn't have to improve performance. Maybe adding the synthetic data actually makes your model worse, so you cannot really know that. And performance optimization is not really the #1 use case for synthetic data generation, usually. So let us start with the imports. We're going to say import pandas as PD. We're going to say from scikit-learn dot model selection import train test split. Where's my autocompletion? There you go. From scikit-learn dot ensemble, I want to use the random forest classifier. And from sklearn dot datasets, I want to use load breast cancer. This is a classification data set, very simple one. Then from the SDV package, first of all, we're going to say from sdv.metadata, we're going to import the single table metadata. This is just important for the initialization. And then from sdv.singleTable, we're going to import the CTGAN synthesizer. So that is going to be the first approach using the conditional temporal generative adversarial network. And the basic example is quite simple. We're going to load the dataset. Data frame is equal to load breast cancer. I'm going to say here as frame equals true. I'm going to get the data frame here. Then we're going to say train and test is equal to train test split. We're going to provide the data frame. I'm going to say test size is equal to 0.2. And now we need to do some setup work for our CTGAN. We need to create metadata. So we're going to say metadata is equal to single table metadata. We're going to detect from the data frame that we have here, from the train data frame, because of course we don't know the test data. This is also important. You never want to do synthetic data generation based on test data because you want to evaluate on unseen data. You're only using the training data for training the generator. Then we're going to say metadata update column. We need to provide the target column here, so the thing we're trying to predict. And we're going to say that it has a certain type, which is going to be categorical. That is the setup work. Then we're going to create the synthesizer. That is going to be our synthetic data generator. That's going to be the CTGAN synthesizer here. We're going to base this on the metadata, and we're going to train this for 100 epochs. And of course, you can adjust that if you want to play around with it, but we're going to fit this on the training data. So I can say synthesizer fit train. So now we're training a CTGAN model to generate synthetic data based on our training data frame. And this didn't take a lot of time. So what we can do now, once this is done, we can say synthesizer.sample, and we can say number of rows that we want to generate now is, you can either go with something manual like 5, and this will generate 5 rows of data, or you can just say I want to double the amount of training data I have. So I will go with length of training data. This is also something you can do. I think it depends on the context what you want to be doing here. But now we have 455 rows of synthetic data generation. This is not real data. This is artificially created data. So now what we're going to do is we're going to generate this and save this. So I'm going to say synthetic is equal to this function call, to the result of this function call. And then I want to say xtrain and ytrain is going to be equal to train drop, and we want to be dropping the target axis 1, and then also just the target is going to be the y data. I also want to do the same thing now for the test data and the synthetic data. So I'm going to do a substitution. I'm going to replace train by test, and that now means x test, y test is equal to test drop target, test target. And here we're going to do the same thing with synthetic. So that's going to be x syn, y syn, and then that's going to be synthetic drop and also synthetic target. And in addition to that, I also want to have a combined data frame. So I'm going to say here combined is equal to pd concat, and I want to concatenate the training data and the synthetic data. We're going to say ignore index is equal to true, and then we're going to split this as well. I'm going to say x combined, y combined is equal to combined dot drop. We're going to drop the target axis 1 because it's a column, and then combined dot target is going to be the y data. The reason we're splitting all this is because I want to evaluate the model, of course, on the test data, but I want to train the model first on the training data alone. I want to train it on the combination of training data and synthetic data. And I also want to show you that just training on synthetic data can yield pretty decent results. Again, no guarantee here that this is going to improve performance, but we're going to see the effect. And sometimes it can improve performance. So let's go ahead and say baseline is going to be a random forest classifier, which we're going to train on just the training data. So that's going to be baseline.fit xtrain and ytrain. And then we can say baseline.score. And we can see that if we score this on the unseen test data, that is going to give us an R squared of 95.61%. So that is the baseline score. Let's now see what happens if we train a combined model. Now I need to say combined model, otherwise it's going to overwrite the data frame. So combined model is going to be equal to random forest classifier, and this combined model will be fitted onto x combined and y combined, and we're going to score it here as well. So combined model dot score on x test and y test. Again, for all these models, this is unseen data. Here now we actually get worse performance. We can run this a couple of times and see that the results are going to differ, but we can also see how well the model performs if we're only training it on the synthetic data. So we can say here synthetic model is equal to random forest classifier, synthetic model dot fit x syn y syn, and then synthetic model score on x test and y test. And here we get 72%. This is much worse. So let's run this again and see if this changes over time. This can be different from run to run. So now this is interesting. We have a baseline of 97%. We have a combined performance of 98%. So this time it improved, but the synthetic model itself only gets 31%. So this can also happen. We can run this one more time here. And we see this time nothing changes here in terms of performance. This gets 60%. This can be very different. However, we also talked about the fact that using the variational autoencoder here can be more reasonable because we don't have a lot of data. So that can also be a reason. And also here we have a lot of numerical attributes, we don't have, or features, we don't have too many categorical features, so maybe here the variational autoencoder makes more sense. And the great thing about this package is that the only thing we need to change is the class. So what I can do now here is I can say TVAE synthesizer, I can import that, I can replace that here so that we're using this class instead, and I can run the entire thing from top to bottom. And let's see what we get here now as a performance. This time we get much better numbers here for the synthetic model standalone. We still get worse performance in this particular run here, but just the synthetic data here alone achieved 91%. So think about this. We have data that is completely synthetic. It is not real data. We're not using the real data set, but training a model on this synthetic data and evaluating it on real test data gives us 91% R2 score here. Let's try this one more time because at some point we're probably also going to get better performance than that. Okay, I cannot get to a better performance right now, but we can see here the baseline very strong. The combined model doesn't change at all. And here the synthetic model has 97% R2 score. Now, let us analyze the data a little bit more. So let's not focus just on the performance of the models because we said that data privacy is also important. So if I take a look at the training data, which is real data here, if I say train head, we can see that this is our training data, and it contains real data rows that might be sensitive. If I look at the synthetic data, we can see that we also have the same sort of data here, but this is completely synthetic. So no real person has this sort of tumor in their body. And we can see that if we look at the statistical pattern, so if I say train.describe here in pandas, and if I say synthetic.describe in pandas, that we're going to see similar statistical patterns. So we see roughly the same mean, we see roughly the same standard deviation for the various features. This is similar data. It models the distribution of the real data. If we do this with a CTGAN with only 455 items, it's not going to be that good. So if we don't do the TVAE, but we actually do the CTGAN again, we're going to see that these numbers are going to differ much more. But you get the idea. We can generate data with the same statistical patterns and do machine learning on them. Now you can see here the mean is quite different. We have different means, different standard deviations. This is not as powerful as a TVAE because we don't have a lot of data. Now, another thing that we can do with synthetic data generation is balance the classes. So instead of just generating any synthetic data here, we're going to generate specifically data that balances the target classes. So if I go here to my training data, I can say train and target, then you will see the values. And if I say value counts, this is going to show me that I have 170 zeros and 285 ones. So this is imbalanced. And now what I can do is I can say generate data so that this becomes balanced. So for this, let us go back to the variational autoencoder just so we get better performance. Let me run this again because now we have a different split. Now we have 166 and 289 here. And we're going to generate synthetic data, but this time I'm going to generate more because remember the variational autoencoder doesn't have the conditional capabilities. We cannot force the target class to be 0. We cannot do that in as a functionality of the architecture. So we're just going to generate 5 times the amount of training data, and we're going to filter specifically for the minority value here. So basically I'm going to do this. I'm going to say minority is just the target value that has less instances. In this case, we can also hard code this as 0. So minority is basically 0. And then we say needed is going to be train target value counts max. So how much do we have here? How much do we have here? It's just going to be the difference. So if we want to hard code this, we can also just say in this particular case, needed is going to be 289 minus 166 if you don't want to write the code. But we can also write this code. I'm going to comment it out for now to keep it simple. That is how much we need. Then we can run this cell. And when we go down to the concatenation here, we're not going to say this. We're going to say combined is equal to PD concat. Basically the same, but here we have the condition synthetic, where synthetic target is equal to minority, and we're only interested in the first needed. So the first number here, the first number of needed instances. So that basically means we're balancing actively the data set. Minority is not defined. Okay, actually I need to say minority. Actually, let's use this code here. Let's do it like this. And now I can train the baseline. I can see what the baseline is, and then I can also evaluate it. In this case, no performance improvement. Let's try again. And after the third try here, we get a baseline of 95, and here we get 96.49, which is an improvement. And we can also see that if I take a look at the combined data frame, and if I say target value counts, that's going to be 286, 286. So we have exactly the same amount of instances with 1 and 0, but of course a lot of these are synthetic. Now let me also briefly show you how we can do that with the CTGAN. So instead of doing this filtering, we can also actually use a condition. So for that, I'm going to import from sdv.sampling, import condition. That is going to allow me to use a condition with the CTGAN architecture, and we're going to keep everything here the same. But here this time, we're going to do the synthetic data generation down here. And before that, we're going to define a condition. So the condition is going to be equal to condition. Number of rows is going to be how much we need as an integer. I'm not sure if this is necessary, but let's say int needed. And the column values that we want to specify here as a condition is target has to be minority. And then I'm not going to do this. I'm going to say synthetic is equal to synthesizer dot sample from conditions, and I'm going to provide condition in a list because we can have multiple conditions here as well. So this only works with the CTGAN. This now works here. Then I'm going to just go and use the old way of just concatenating the two. And if I run the same thing here, no guarantee that it's going to improve. In this case, it doesn't, but the value counts are also equal again. If I may for a second, I would like to plug myself in as the sponsor of my own video. If you go to my website, neural9.com, you will find a tab services and a tab tutoring. Here you can hire me for all sorts of stuff like data science, machine learning, web development. If you need help with something in a project, here you can book me for one-on-one tutoring if you want me to teach you personally something that you don't understand. If you like my teaching style, on both pages at the bottom, you can contact me via mail and also via LinkedIn. Just wanted to let you know about this. Now for the last two examples, I want to go through them quickly, so I'm not going to type them from scratch. I'm going to copy paste them and discuss them with you. The first thing is rare case training. What does this mean? Here we have the same setup as before, just we have the California housing data set. So this is a regression task now. We're using a random forest regressor, not a random forest classifier. Here we have a TVAE synthesizer that we're using. And specifically, we're defining rare cases in the data. So a median house value above 4.5. This is just a rare value in the data set. It doesn't exist that often. And what we do here specifically is that we use from the training data only the samples or only the rows where this condition, this rare condition is met. And then we train a synthesizer only on this rare data. And then we generate 1,000 of these rows. So we generate synthetic data that only models the distribution of this rare data that we have here. And then I augment the data. Maybe augment is not the best word, but we add the rare data, the 1,000 rare data rows in addition to the training data. And in this case, we even get better performance. This time we're looking at mean absolute error. So this is actually better if it's a smaller value. And here we decrease the error by adding this additional synthetic data to our training data set. Specifically though, we also can evaluate this on rare data. So we can get from the test data, the rare data, and see which model performs better. The one that was trained on augmented data or the one that was not trained on augmented data. And in this case, we also get performance improvement. If we're only focusing on the rare test cases, our model with the synthetic data performs better than the baseline one. And then finally, I want to show you how to do edge case testing. This basically means we have a similar setup here, California housing random forest regressor, but this time we don't use it to generate training data, we generate test data. So we want to see how does our model react to data that I don't have. So maybe I don't have the data where the median income is in the 99th quantile or percentile, where the average rooms are very low. I want to generate 10 such rows and see what my model will do, and then decide if that's an intelligent move, if I want this to be how my model reacts, if that is what I'm expecting from my model. In this case, it predicts a house value that is quite high, upper end of 3 point something is pretty decent, I guess, if you have that little rooms and a lot of median income. And if you want to take a look at the statistics, you can say ytrain.describe and see what the data looks like and if it makes sense to you. So that's it for this video today. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab that you can contact me if you need help with a project, if you need a freelancer, a consultant. You can contact me at the bottom of both pages using LinkedIn or via email. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.